Okay, here we go with our next review video. We're going to take a look at the information in our review packet. What I'm going to do is I'm going to do some work over here and leave room for some work for problems off to the side over here. So the next thing we're going to look at are parametrics, which don't happen that often in calc tests, but we're going to take a quick look just in case. A parametric function is when x and y are defined by a separate variable, usually called t, and time is our independent variable, and they'll ask me to find dy dx. It's really not that hard. It's very straightforward. Dy dx is equal to the derivative of dy dt over dx dt. So the 6 cosine t, and dx dt is going to be negative 5 sorry, sine of t. The biggest problem with these is that dy dt goes on top, and usually it's written on the bottom of the problem. And that's where people often tend to get that wrong. Only thing we have to do is if they ask us to find the second derivative, I can't just do that rule again. I've got to use this fraction right top. So it's going to be 6 cosine t. V is going to be negative 5 sine t. So u prime, it's kind of small to write it in here. I'm going to put it down here. It's going to be negative 6 sine t. And v prime is going to be negative 5 cosine t. The trick on these is the minus signs and stuff are going to change often. So when it gets filled in as, I'm going to write it off to the side here because I can't really fill it in. Do we have enough room? Let's try. Now let's write it here. Negative 6, you can fill it on the paper if you want. Negative 6 times t, that's u prime v. Negative 5. Ooh, that's not enough room. Which would be negative 5. To be there, let's spend time on the next one, which is line, linear line to estimate f of 3.01. Okay, but they want us to put the line at x equals 3. So if x equals 3, I know that f of x is 6x squared. I know that f prime of x is 12x. That means that f of 3 is going to be 3 squared, which is 9, times 6, which is 54. I know that f prime of 3 is going to be 3 times 12, which is 36. Hopefully I got that right. So my local linear line, L, is equal to f prime of c, x minus c, and f of 3 value. And when they give us that line, the line and the curve, what happens is if this is the point where it was, the line and the curve, this would be 36, x minus 3 plus 54, are exact at that point and close at values next to each other. So f 3.01 would be about the same value as if I put it into the line. 36, 3.01 minus 3, plus 54. Now normally they have you do this without a calculator, but you're going to have the calculator, so watch what happens. It's approximate. It becomes, so 0.01, 3.01 minus 3 is 0.01, 0.01 times 3.6 is 0.36, plus 54 equals 54.33. That value to the other one that's there. And this is going to come up a lot. As a matter of fact, in the review, we're going to do some more of these. I'm actually going to pause and go to the spot where they right now we're on page 13. I'll give you the page number in just a moment. Okay, this is on page 41. If you can turn to page 41 in the packet. It's just another example of this same type of problem in which as soon as they ask us to find, I'm going to use the function that's already there. As soon as they ask us to find a local linear line or a tangent line approximating the curve, 15 minus x to the third is the one we're going to use. First thing we identify is what our value is. Our value is 2. And we know f of x is 15 minus x cubed. And that means that f prime of x is negative 3x squared. We then put 2 into each of those. So I get 15 minus 8, 7. I put 2 into there. 2 times 2 is 4, times 2 is 8. That's how I got that number there. And f prime of 2 is going to be 2 squared which is 4. 4 times negative 3 is going to be negative 12. So my local linear line, L, is equal to, forget your derivative, x minus 2, and forget u, the actual value. And if you just double check the problem and you're doing it here, your point on the graph was 2. That's where that is 7. And the slope at that point was negative 12. That's where those numbers come from. They all fill in there. And then the line is used to approximate the actual curve. So we can use the line to estimate values at 1.99 and 2.1. I have to be careful to use these correct symbols. The value of the graph at 1.9 is approximately the value of the line at 1.99. Negative 12, 1.99 minus 2 plus 7. And the value of the curve at 2.1 is approximately the value of the line at 2.1. Negative 12, 2.1 minus 2 plus 7, and you can see I can fill the values on in here. This is the easiest one to do right here because it becomes 7 plus, 7, I will do plus minus 1.2 because this becomes 0.1 and the decimal moves over one place, which equals 6, 5.8, and then the 1, this becomes negative 0.01, so it becomes 7 minus a minus plus 0.12, which equals 7.12. That's the value on the line that approximates the value of the curve. Pause that for a moment. Okay, good work on locally linear lines or tangent at a point. Back to derivatives. Remember, we're going to be doing implicit differentiation. Whoa, there it is. Implicit differentiation means you need a prime. Unless it's time, it just means that you can't get the variable by itself. And when you take its derivative, you're going to have to include a prime on all the answers. The standard algebraic version of the problem looks like this. There we go. So I would take the derivative of this, which would be x is my independent variable. So it would be 2x plus 2y. Derivative of 9 is nothing, equals 0. Now, the reason I did it that way was just to show you in one example. When I take the derivative of something other than the independent variable, I've got to include a y prime on there. Technically, that y prime is equal to dy dt. It's the shorter way of writing it. Oh, dy dx. Sorry, based on x. There is actually one that's here in this spot. It's x prime, which is dx over dx, which is 1. That's why on the independent variable we don't add anything in. And now we work to get y prime by itself. I'll subtract 2x. 2y, y prime equals negative 2x. Divide each side by 2y. And where we have it, y prime equals 2x over 2y. Don't do any simplifying if you don't have to. The next version of the problem is when you see two things in here multiplied like this. This problem looks like it's going to be really easy. It's 2x here. Right here, it becomes 6y, y prime. And this part becomes 0. And everyone thinks that this part is a simpler part, but actually a product rule. Arg. So I'm going to fill it in right here. And the product rule is going to be, that's my u, and that's my v. So plus u prime, v, plus u, v prime. The derivative of y is y prime. And this answer is totally fine. You can leave it like that. If they ask you to get y prime by itself, I don't think they will, but if they do, the trick is if you have everything on one side, leave the things that have the y prime in it. Move the other things to the other side. Negative 2x, negative 2y. And then whatever's left on these, you just put on the bottom as divisors. 2x is a positive, plus 6y. I know I did that kind of the short way. It really is these things get subtracted to the other side. And then what's happening here is I'm actually taking these pieces. I'll show you what I'm doing. I'm actually factoring out a y prime. And then this gets divided to the other side. Okay, some problems you won't see the independent variable, or they'll tell you about it. For example, if they tell you the independent variable is t, and you don't see it, we're going to, instead of using symbols like y prime, we're going to do 2x dx dt. And the difference between this problem and this problem here is they'll tell you it's based on time. Plus 2y dy dt equals 2z dz dt. Other things are based on time, like this problem right here. So I took the derivative of this one with implicit differentiation, dv dt equals pi. Now I've got a problem. I've got a product rule right here. R squared is one term, h is the other. So the derivative of r squared is 2r dr dt. That's u prime v plus u. And the derivative of h is dh dt. We're going to see more of that coming up in just a minute. So I'm going to talk about this last part right here of this video, which is derivative of an inverse function. I'm going to pause for a second. I'm going to give you a description over here. It's going to come up. I'm going to show you a quick example, and then I'm going to show you the shortcut to finding the problem. So I'm going to give you a description. I only have a minute and a half to record on the video of where this rule comes from. Please remember that if you take a function and its inverse, and you apply them both to a problem, you get the original problem back. I'm going to take the derivative of both sides of this equation right here. So this is equal to 1. Now this is a chain rule. So the derivative of the outside, which would be f prime, don't touch the inside, negative 1 of x, times the derivative of the inside, which would be the derivative of the inverse of x. So in this problem, they're asking about the derivative of the inverse function. So what I'm really looking for is this piece right here by itself. If I were to divide the other part to the other side, x equals 1 over the derivative of the inverse of x, which is actually what it says over here. That's just the proof of how it gets there. The proof isn't going to help you out. I have a shortcut for doing these problems. And if we hear the word derivative of an inverse, as soon as we hear inverse function, we're going to do the flip. It just means I'm going to flip both things. If I'm starting with an x, I'm going to change that to a y. And if I'm starting with dy dx, I want dx dy, so I'm going to take. I'm not going to be able to finish in this video. I'm going to have to record to the next one. I'll see you in a few minutes.